So the remainder of the afternoon is going to be focused on this topic of treating forages with chemicals. We'll get started off with a little bit of a brief history of why this came about. Some of the current research is what Adam's going to be presenting. Following that, there's going to be some more demonstrations from some of the industry people here. So I don't want to spend a lot of time on giving an introduction. I think the previous presenters were able to do this effectively. But the availability of the residues, I just want to reiterate that we can utilize those better. Klopfenstein discussed about using these in forage diets or growing diets or cow diets, but it may have some, we may be able to increase the concentration in the finishing diets. For a brief history of this, the chemical treatment actually began in the 1880s. What it started as is the pulping process to make paper. And what they noticed is some of those reagents that they were using to produce the paper were increasing the digestibility of the cellulose of those high lignin content fibers. And so there's been several different types of chemical treatments that have been evaluated. Alkaline treatments would be your strong bases, some peroxides, and something that maybe several of you in the audience is more familiar with is ammonia treatment of these residues. So similar to what Galen discussed and what Dirk discussed about higher levels of corn silage, there could be a lot of potential synergy with including this treated forage with the distiller's byproducts. That's been shown time and again. Galen did a good job describing that there is decreased performance and there could be higher cost per unit of energy with these residues. There hasn't been much data recently with the exception of these 3 states. There might be a couple other states that are getting involved with this, but there's limited research on the feedlot side. One of the first methods that tried to perfect this system was the Beckman method. It was in the 1920s. They used a strong base, sodium hydroxide, and what they did is they filled the tank with enough water to cover the residue that they put in there. And they let that soak anywhere from 18 hours to 3 days. And what they had was a 2-tank system where they'd take this very strong concentration of sodium hydroxide, which was caustic, and they'd drain that to another tank, and then take that first tank with the residue in and add volumes of water until they got excess sodium hydroxide. And what they found is that with rye straw, it actually increased the digestibility. It was rye straw, increased the digestibility from about 46 to 76%. So a large increase with this chemical treatment. The problems or the challenges with that, it had a very high water requirement, and that excess sodium was actually just rinsed away with the wastewater, and that presented some pollution challenges. Because of the high water requirement and that flushing to remove the sodium from the residue, they also observed that they had very high dry matter losses. A lot of the cell solubles, some of the solubilized hemicellulose in that treated residue actually left the system or was washed out, and that was from 20 to 25%. Now this was one of the first methods that was used, and since then the modifications improved the feasibility of this in several different systems. And some of those are also from combining sodium hydroxide and calcium hydroxide. So our department head was asked to give a review at the animal science meetings this last March, and what Dr. Berger found was that with sodium hydroxide treated roughages or residues, that it increased dry matter intake about 22%, and over several studies, dry matter digestibility increased 30%. So quite large improvements in these low quality roughages. When you compare that to what some people here, probably several people here have done ammonia treatment, just to compare the base or the alkali treatment with ammoniating these residues, intakes over several studies that was averaged was around 22%, which was similar to the sodium hydroxide. And that dry matter digestibility didn't increase as much, but it was at 15% compared with the non-treated residues. One of the reasons why this isn't as popular today is because the price of energy went up, the price of the anhydrous ammonia went up, and since we only retain about a third of what of the gas that was applied to those residues, it didn't seem like a feasible option, and that's why it's not done commonly today. And there's going to be challenges with any system with ammonia treatment. Temperature, water content, and the length of the reaction time all has a factor on the effectiveness. So I just briefly want to outline some of the differences between the different compounds that are available that have been shown to increase digestibility of these residues. The hydrolytic or the alkali are on the left-hand side, and the oxidative on the right-hand side. I don't know what the availability is of some of these compounds, like ozone, but they have been researched well in the past. As Galen mentioned, some of this stuff has been done many years ago, and what they did find is that those two different types of compounds have a different effectiveness or act differently on the forages. But overall, the goal between the two types, oxidative or alkali or hydrolytic, was to disrupt the polysaccharide lignin association. Once that gets disrupted, you have more enzyme accessible space. So with hydrolytic, there is partial solubilization of the hemicellulose. At higher levels, above 5% sodium hydroxide, some lignin and silica was solubilized. It also disrupts some of the intermolecular hydrogen bonding. So I have a couple cartoons that Luebbe Shreck put together that I'm going to show that just kind of gives us a visual of what has actually happened in those plants. With adding sodium hydroxide, it helps to increase the rate of fiber hydration. If that fiber is hydrated, it gives the bacteria, it doesn't take the bacteria as long to colonize and start digesting those plant materials. So it kind of decreases the lag time. For oxidative, similar concept, but just slightly different effects on the cell wall structure with the lignin. Increases soluble carbohydrate again, but it was found that it's usually more effective, the oxidative treatments, with dicots than monocots. And that's just due to the different structures of the plants, where if you have a highly lignified concentration in dicot, even if you do use some of the higher levels of the sodium hydroxide, because of the chemical structure in the plant, you won't have the same results. So this is a cartoon of hydrogen bonding and the so-called crystallinity of the fiber. With these alkali treatments, the hydrogen bonding, those red bars, it decrease, which increases the bacteria's enzyme accessible space and increases digestibility. This is another way of looking at it, and I like this cartoon that Adam put together, is if these were cells, plant cells, and the cell solubles are in the middle with hydrogen bonds, after alkali treatment, the bacteria are able to get in there and start degrading more of that material. So as I mentioned before, there were several studies, and a lot of them were before the 1980s with either sodium hydroxide or calcium hydroxide. And as a generalization, sodium hydroxide did have an improvement in digestibility over calcium hydroxide. But a combination of the two did seem optimal, and it was actually greater than the sodium hydroxide alone. So there was a little bit of synergy there. But some of the challenges with sodium hydroxide and why people are talking about calcium oxide or calcium hydroxide is that the cost of the chemicals is going to be great. You can have an increase in the amount of sodium that's in the manure, and that could pose some challenges if you're not spreading it over enough fields. And one of the main reasons might be the safety and the handling of having that strong base sitting around a feed yard in a production setting. Length of reaction time can be a challenge, storage, and overall feasibility in some larger operations. So a lot of the current focus has been on calcium oxide, and I want to stress it's not calcium hydroxide, so it is a powder. It's also known as quicklime. It's much less caustic than other treatments, and I think some of the other presenters later will discuss some of the safety precautions that are needed, but they're far less what is needed if you're handling a strong sodium hydroxide solution. We see there's an improvement in digestibility. There's no detrimental impacts on fields that are receiving the manure. And really, if you're adding that much calcium as calcium hydroxide, you can just remove a portion of your limestone that's in your diet. We think that, I don't know if there's any good direct comparisons between calcium hydroxide and calcium oxide, but as in a couple more slides, I'll show you that there may be a little bit less heat produced when this is mixed with water. So we're not sure if they are going to be equal. When you add calcium oxide and water, it releases about 65 kilojoules per mole of energy. I didn't know what that meant when I was standing next to a feed bunk, so I had to put it in terms that I was familiar with. So if you add 2 parts of water and 1 part of calcium oxide, that solution would have enough energy that it would start to boil the water. So there's a strong release of heat. That's why they term this more of a thermochemical reaction than rather just a chemical reaction, because you get the combination of the heat and the releasing of those bonds. So I'm going to summarize a little bit of some of the preliminary work that was done with calcium oxide that Adam did. There are several experiments that were evaluated and many different factors. I'm not going to spend time going through there, but just as a generalization, some of the more important factors to make this feasible in a production setting were evaluated. Dry matter, how much water do you need to add to the residues? What chemicals to use, the reaction length, how long does it have to be stored before it's fed, what temperature do you need, and also forage type. So, brief summary of several experiments with the chemical treatment with calcium oxide and sodium hydroxide. They did find some synergy using combinations of the two. But really, there's not that large of a difference between calcium oxide alone. And because of the handling and the safety issues, this appears to be a pretty good route to take. Dry matter, it seemed like 50% was optimal. And Adam's going to share with you how this was done with the research that was conducted here at Meade. And later, Casey Mackin and Mike Sakeva are going to talk about some larger scale application and what constraints they have. Temperature relative to room temperature, starting with the starting materials, it didn't seem to increase the reaction. Usually when you increase the rate of reaction 10 degrees Celsius, it doubles the reaction. But really, they didn't find a large increase with warming up the solution. And one of those reasons may be because of that strong release of heat is already present. And they also looked at optimum treatment length, and they determined that 7-day treatment was ideal. So before I turn it over to Adam, some of the rules of thumb that the previous authors in that review that Berger did back in the 70s, they said that the pH needed to be above 8. You wanted to be basic. We do have some data that Adam will share that that's not a hard and fast rule. It's a good rule of thumb to stick to, but that might not always be the case. When we talk about storage of the residues between the time you treat it and the time it gets fed, I don't want to confuse you with what we say storage, bunkering, or putting in bags. Our goal is not to ensile it, because if we ensile, that fermentation decreases pH, and it doesn't help with the system. You end up with something more of a neutral pH, and the effectiveness is much less. Since we have had several questions about this, both Galen and I have both discussed this over the phone, and some producers believe that, well, if I'm going to feed it with byproducts because we believe there's a synergy with wet byproducts, that adds my water. I can have one trip to a bunker or some storage area, but what needs to be kept in mind is that distiller's grains is fairly acidic, and it's counterproductive to what you're trying to do with these alkali treatments. So I think I'm going to go ahead and turn it over to Adam. As I mentioned before, this is the first out of 3 this afternoon that we're going to talk about this concept. And there may be some different applications that you want to save till later, but we'll try to address some of these questions now.
Okay, thank you, Matt. My name's Luebbe Shreck. I'm a PhD student under Galen and Terry. And first, want to point off that cartoon you observed, rumen bacteria do not actually look like Pac-Man. But getting into our treatment process, we initially will buy residue in bale form, be it wheat straw or corn stover, and then we will grind that with our Mighty Giant hay grinder. We have typically worked with a 3-inch screen for grinding, and we can easily push 10 to 20 dry matter tons per hour while grinding that. The next step in the process is we add calcium oxide and weigh up a known quantity of residue in the feed truck. So it's important to know the dry matter content of the residue, and we add calcium oxide at 5% of that. So 5% calcium oxide, 95% residue on a dry basis. Calcium oxide that we've been working with is the granular standard quicklime. It's a very fine particle size, 1/4 inch to essentially dust in diameter. Very high purity product, and from what I understand, there's very many types and kinds and even higher levels of purity that is retailed, and this is the kind that we've been working with. So it's a dry, granular powder. If you do the math on a molecular basis, it should be about 71% calcium. And the cost of this product, some will know better than us, but we've been hearing that the cost is somewhere in the range of $320, $350 a ton. 4th step in the process is adding the water. So we would load the stover and put that in the feed truck, and then usually it takes about 50 pounds of this material per load of what you can get inside of a Rotomix, and then we'll layer that on top, and right before we put water on, we'll start mixing it, and we calculate and target a 50% dry matter mixture. And very important to get the right and correct amount of water on, 1, from a safety concern, and 2, really there's a kind of a balancing act, is what Matt showed, with adding the proper amounts of water. It will enhance the treatment process, and if you add too much water, probably going to encourage some type of fermentation, which we know is not conducive to this process. Last step, mix it up in the feed truck and discharge it into an ag bag. We've been storing these anaerobically. Usually we will make up our needs for a trial or for the feeding period at the beginning, and bagging and storing these. It's important to point out it does not need to be stored anaerobically for it to work. However, if you're going to be storing it for large amounts of time, you're going to have some mold if you store it outside. Other systems, as we'll probably see, working on a pile system where they store it outside, and as long as you have it sit for at least 1 week prior to feeding, that's the minimum length of time needed to ensure that the treatment process is complete, get along quite well. So getting into the first study that we conducted in the spring of 2010 with some yearlings, our treatment design, we had a control diet that contained 46% dry rolled corn. We had 40% wet distillers grains in all of these diets, and a little bit goofier kind of a roughage that we had, but it was what we were working with at the time. Our roughage comprised 10% of the ration, and it was made up of equal blends of untreated corn cobs, untreated wheat straw, and corn stover that had just been ground and stored dry. We compared this control diet to replacing 10 percentage units of corn. So we're comparing 46% corn in the control to 36% corn in these diets that we tested. And also, we're doing that by including 20% treated or untreated residue, be it wheat straw or corn stover, as you can see. And that's also obviously accounting for supplying the roughage in the ration as well. We also made the comparison of corn cobs, either treated or untreated. Did not show the data here today. Didn't get a response. We're not sure why on a performance-wise, but the details of this experiment are in the 2012 edition of the Beef Report. Looking at performance, we had a 3.8 average daily gain for the control cattle, and similar, and if anything, a slight numerical increase in gain for the treated wheat straw, but wasn't significant. Very comparable amounts or average daily gain, and not significant compared to the control for treated corn stover. Didn't pick up a difference in intake in this study. That led to similar feed efficiencies that kind of follow the gain, as you can see, as far as their relationships to one another. That was carcass adjusted performance. We've seen similar trends in carcass weight. Notice how much that the untreated residue inclusion dropped off quite dramatically, as you would expect. Had similar amounts of 12th rib fat for the diets containing treated residue. Similar amounts of marbling was observed as well. So we've had that experiment, and we thought as going forward, maybe there's things we can do to really enhance the value of this treated residue. Maybe one idea we had was to grind it smaller prior to treatment. So we got this crazy idea of grinding stover through a 1-inch screen. It was good dry stover, and we had plenty of time to get the job done. And we did grind stover through a 1-inch or 3-inch screen. That was our other comparison, and then included that in the diet at 20%. We went through a little bit stronger control. Control is probably more commonly fed in Nebraska. Had 5% untreated 3-inch ground stover as its roughage. And all these diets, we had wet distillers in the last experiment. We had modified in this experiment, and that was at 40% of the ration. Looking at performance, we've seen similar performance for the 3-inch treated compared to the control. So that said to us that yes, you can replace 15 units of corn, and this was done with some heavier calf feds. But we also noticed a slight, subtle improvement in performance with grinding the stover smaller prior to treatment with the 1-inch grind compared to the 3-inch grind. Carcass weight, very similar to performance. That carried over there as well. Similar amounts of 12th rib fat, similar amounts of marbling, and percent choice. Didn't show the data, but those were similar as well. So those two experiments were conducted, and then about the same time we had an opportunity to kind of look at some mass balance work and some manure work, kind of what Galen was talking about. Maybe we could increase organic matter in the pen surface and trap nitrogen. I'm just going to talk about the performance data today. But we had a separate set of calves that we made the dietary comparisons similar to what I just presented. Only these just had 3-inch ground treated or untreated stover. Again, a control diet that had a little over 50% corn, equally split by high moisture and dry rolled, and 40% modified in all these diets, 5% roughage, and the control still replacing 15 units of corn with this comparison. These were a little bit lighter weight calves entering the feedlot than the grind size experiment I just presented, but they had similar intakes, similar average daily gains, comparing the control to the treated. Untreated cattle had lower average daily gains, as you would expect, and very similar feed efficiencies were observed for the control and for the treated stover cattle. Big decrease in efficiency with untreated. So we fed these from November to May, and as soon as we could get the pens cleaned, I'll show you the performance or the carcass here. Similar carcass weights, and actually had similar dressing percentages as well, which might be was somewhat unexpected because we're feeding more roughage, so to speak, in these diets. But we didn't see a depression in dressing percentage in this experiment comparing the control to treated. It did drop off with the untreated. Similar amounts of rib fat and marbling as well. And as I was saying, we followed these right behind with some yearlings, and we've conducted 5 studies, and this has been the only one where we've kind of lost some performance by treating the residue compared to a strong control. We had similar dry matter intakes for the control and the treated, somewhat numerical increase. Combining with that, a not statistically different but somewhat numerical decrease in average daily gain led to a statistical difference in feed efficiency, with the treated residue or stover cattle having poorer feed efficiencies than the control in this trial. That carried over to lighter hot carcass weights, and actually we did have a decrease in dressing percent with this set of cattle of the treated having lower than the control. But we did have similar amounts of 12th rib fat, similar amounts of marbling, similar amounts of percent choice as well. The 5th study that we just conducted has kind of a complex treatment structure, but we were really trying, the whole goal of this experiment was to we've had success with replacing 15 units of corn with treated residue. We've had success with treating stover or treating straw. So how far can we really take it? One idea or one question we had was, especially on the dairy side, there seems to be some kind of almost requirement, if you will, or a minimum amount of starch or corn needed to support performance. And we kind of thought that might be true here as well. And so we had increasing corn levels in the diet at 10%, 25, and 40. And then the balance of the rest of the ration was being replaced by a 2-to-1 ratio of modified distillers grains and treated residue. We had a couple of different sets of treatments. We had treated stover that was at a ratio of 2-to-1, and then kind of factorialized with all these different corn levels. And then we also had a 3-to-1 with treated stover, and then a 3-to-1 with treated straw. So our the rest of the ration is varying anywhere from 18 to 25% treated residue, and anywhere from 40 up to 65% modified distillers grains in the diet. What we found was that as you increase corn, particularly in the treated stover diets, we did see improvements in linear decreases in feed efficiency. However, we also noticed that comparing a higher blend of modified distiller's grains to treated stover, we did see an increase in efficiency, and really interestingly was what we observed with the treated straw. It didn't present average daily gains. This was done with an individually fed experiment, so we didn't have a great deal of power or ability to detect differences in this trial. But if you look, we also had the 10th diet, and we had a control that was included that was a very typical control, 35% modified distiller's grains, 5% roughage, the rest being dry rolled corn and supplement. That control was at 6.89, and as you can see, very similar conversions as you get 25% corn or above. So that would say, so taking from this trial, it would say to us that there's easily a maximum of 20 to 25% inclusion of treated residue that you're going to have in the diet to support performance comparable to a regular control. At least 25% corn is needed in the diet as well. And if you have the opportunity, you can replace a little bit more corn with distillers relative to treated stover than just treated stover alone. We get a lot of questions about what can I use for quality control measurements? How do I know that the treatment process has worked, and how do I know that it's working well? That's probably the hardest thing to do, but if you can, the best thing you can do is to have a sample of the original untreated residue. That kind of gives you a baseline of where you're at. Once the stover or residue has been treated, there's several different measurements that you can look at. One of them I discussed is you can dry matter that. It's something you're probably going to do anyway. That lets you know how well the moisture is being applied. Very important. Secondly, probably assaying for the amount of calcium that's present in the diet to determine how well or uniformly that's getting mixed. The pH of the material itself, I'll show in a little bit how that kind of changes throughout the feeding period. And if you have the original sample that you can compare to, the amount of NDF that's solubilized or not recovered kind of gives you a good diagnostic of how well the stover process occurred. And you can only make that comparison if you have the untreated. Also, if you have access to getting a sample analyzed for in vitro digestibility, that's also a pretty good idea as well. And just to kind of point out, we all send samples into the lab. They give us a very nice printout of every nutrient under the sun. Along with that, they give us estimates of energy content, and you need to be very careful about taking those for what they're worth. The assumptions and the calculations that go into assuming that energy content, if you send a sample in, are based on different things and may underestimate the value of this. As Matt said before, this process really doesn't affect lignin very well, or just doesn't really affect it at all. And a lot of those calculations based on energy are based on lignin content. So it may tell you that it's just no better than untreated residue. As I said before, we get quite a bit of NDF that's solubilized compared to the original untreated to the treated. As a percent unit decline, anywhere from 11 to 18 percentage units of NDF we're not picking up when we run it. So as a percentage change, that's 13 to 21% decrease in NDF, so to speak. It's still there, it's just not being recovered. Looking at pH, the top graph is treated stover that we did a while back. So this would represent untreated stover. It's about 6.5 to 7 pH just by itself, just after it's been ground. When you add the base of calcium oxide, that will raise the pH. Sometimes it will raise it even higher. But what we observed in this trial is it raised it close to 9. And then we followed this clear out to 11 days post-treatment. And it's, for the most part, there's some variation and some noise in here, but for the most part it stays about 9 for at least that time period that we followed this sample. If you look at stover over the whole feeding period, so if you're feeding cattle, or you got cattle on feed for 150 days. We followed some stover and some straw. It started out at between 8 and 9, and it decreased slightly, but not very much over the whole feeding period, probably indicative of some low level of fermentation going on. Same way with straw. Similar results that we observed over here in 2011 as well. So another thing people ask is, what's the value of this, particularly as it relates to energy? We have some comparisons that we can use to kind of estimate its value. We have in vitro data with straw and stover that's in a test tube and using rumen fluid, or in vivo data using animal digestibility. And in each case, the percent increase was pretty dramatic. This is, and one important point here, this is in a finishing diet. This is at 25% inclusion, and we've seen a 52 and a 73% increase in its value of organic matter digestibility. So as Dirk kind of led on, there's likely some synergy not only between byproducts and corn silage, but also it's probably not outside the realm to think that there's some synergy here as well. The hard part in estimating energy value is, what do you estimate untreated residue at initially? We have some data to suggest that it's pretty close to 41 TDN. So if we assume that number and we take those percentage increases and we multiply that by the starting value of 41, we're getting TDNs anywhere from 69, 62, 70. So a pretty dramatic increase in TDN content of untreated to treated. I know many of you are interested in growing situations in cow-calf backgrounding type places. We don't have great data on what its value in that type of setting is. But if you look at the old historical literature where they took untreated residue and fed that as most of a ration to cows or to growing calves, you only see about a 10 to 15 unit increase in TDN, a much smaller increase than what we're predicting here in a finisher diet. Another way to look at its value energy-wise is, well, we replaced 15 units of corn, what's its value to corn? And right away you can kind of say, well, it replaced corn, you got similar performance, so it must be as good as corn, right? Well, not necessarily. What we did was we used the NRC model and used our control in each study as kind of a benchmark, and we matched and got its performance lined up using the net energy maintenance and NEG adjusters. And again, we had to assume a few things for energy content, but we're pretty confident about these. We used 112, 118 for modified and wet distillers, 125, 130% the value of corn. Again, we assume that corn, stover, wheat straw was 41% TDN and book values for corn. So using that, we got TDN values across these for these different experiments that I presented. We got TDNs anywhere from 62 to clear up almost to 80, depending on the study. The interesting thing to point out is if you compare those to what we observed digestibility-wise in the animal or in vitro, they're all generally higher. Again, suggesting that and the inclusion level, to be fair, in this comparison is a little bit different than what we've fed in some of these trials, but generally they're higher, so that's pretty interesting. And to kind of conclude here with some economic analysis, it's really hard to kind of put together accurate pricings for a lot of this and what exactly it's going to cost and what exactly it's going to return, but we did the best we could. Depending on what corn is priced at, what we thought was one factor, so we assumed that corn, you could buy it for either $5 or $6 a bushel, and some other assumptions all on a dry basis. If you had the chance to buy stover or wheat straw at $60 or even up to $80 a ton dry matter, which may be high, but we want to be conservative and kind of be on the high end for these estimates. And we're going to assume that after that, you're going to have 10% increase in cost due to grinding and another 10% increase in shrink. We're going to use $350 a ton cost of calcium oxide. So if you're adding that at 5% of the dry matter of the stover on a ton basis, dry ton basis, right off the top, that's $17.50 a ton. And probably the most important thing and hardest thing to estimate is what is the actual labor cost, treatment costs involved, other than calcium oxide. We have limited ability to kind of estimate what this is. We assume that it was $20 a ton added cost for labor and handling and whatnot. So if we assume the grinding and shrink additions to initially $60 or $80 ton residue, you're in for about $75 or $100 a ton dry matter of untreated, that's to the bunk. So treated residue using these increased costs or initial costs, we're assuming that in these comparisons across these 4 different studies that it's $112.50 or $137.50 per ton dry matter to the bunk cost for treated residue. And so we broke it out by wheat straw and stover. Keep in mind, we have limited data on wheat straw. It's something we should probably pursue. We've seen a very nice response to including wheat straw in the one study that I presented. And not surprisingly, if you can feed something cheaper and have a little bit bump in performance, it's going to look good dollars and cents wise. And so even at $5 corn, and even if you're putting in quite a bit of effort and money into treating it, we think there might be some real opportunities for straw, even though the focus of this meeting is with stover. There's many areas of the country you can find plenty of straw. Stover, a little bit different scenario. Again, we have more data in this area. This is something that we've researched more. A slight, very subtle decrease in efficiency. As you can see, the study range, some slight improvement to really most of this. The numbers are being driven by one study with yearlings where we didn't quite have as great a performance. And so this is probably a worst case scenario in my mind. Corn you might think corn at $5 a bushel is not a worst case scenario, but if you think about it competitively compared to a regular control diet with most of it more corn, it doesn't look near as good as it does with higher corn prices, as I'll show in a minute. And you can see the returns here, and there is some range given at this pricing scenario. However, if you increase this to $6 corn, so on a ton basis, corn at $5 is $211 a ton dry matter. So now we're up to corn that's $250. The returns look a lot better, especially for straw. And as you can see, they look a lot better for stover here as well. So future economics, it says to us that really need to have similar efficiency to be competitive in the market. The costs of calcium oxide or calcium hydroxide are very important, and those are big factors influencing the amount of return you can expect on this. Obviously, if corn, we live in a volatile world, especially with prices. What will corn costs be? And at the same token, what will residue costs be as well? And it's very important to make sure that a lot of these decisions are being based on carcass weight, not live weight basis as well. So in summary, including diets that contain 20% treated residue with 40% wet or modified distillers grains, we really think that that's the recipe. Should result in similar performance, carcass characteristics, all at lower diet costs. We have future plans with this work. We think that this is something that's going to be part of our research program as we go forward. So with that, if you have funding opportunities, see Galen. Be happy to take any questions you may have.